This conference will now be recorded.
So, very good evening. Today, we'll conclude this chapter by learning how to derive Kepler's three laws. In the very first class of this chapter, we had discussed Kepler's three laws. So today, I'll recap a little bit of those laws, and we'll learn how to derive all those laws from the knowledge of gravitation or laws of gravitation. So we know there are three laws basically. Okay, so there are three laws. Excuse me. Yeah. So there are three laws we know. So first law is the law of orbit. It says first law is law of orbit. Excuse me. So the first law is law of orbit. It states that all planets move in elliptic orbits with the sun situated one of the foci of the ellipse. So all the planets moves in elliptical orbit, and then sun situated, always situated at one of the foci. There are two foci, like foci. You look here, S1 and S2. There are two positions for the foci in an elliptic orbit that we had discussed in the first class itself. So today we have to prove that how, how we can prove this particular law. That means we have to prove that the orbits of the planets will be elliptic. That we have to prove. So for that, let us take this figure and see. In this figure we have sun over here, sun here, and we have a planet which is revolving around the sun, and sun is one of the foci of this elliptic orbit. Okay, so let us first, actually this first law of planetary motion given by Kepler can be proved indirectly at this stage. Actually, if you go for higher standard study, like in the graduation, there will be, there you will get exactly the equation for ellipse. But here we are not deriving the equation for ellipse, but we can indirectly prove that the orbit will be elliptic and closed orbit. Okay, so let us say there is a there is there is a planet which is revolving around the sun, keeping sun as one of the foci, and the position vector, position of the planet with respect to sun, with respect to sun, with respect to the sun is r, sun is small r vector. So this is in bold letter, that means it is a vector quantity, or maybe I can write even vector notation like this. This is the position vector with respect to sun. Okay, position vector of the planet. Now look what happens. This planet is actually revolving around the sun due to gravitational force. If suppose mass of this is ms and mass of this planet is mp, then the gravitational force or gravitational attraction exerted by the sun to this planet will be F is equal to minus gms mp by r square. Okay, so and this is along the r vector with a minus sign. This is the vector notation in terms of vector notation, because we know the force, gravitational force is attractive force, and it is always acting towards the center of the sun. And look why r cap with a minus sign, because the force is always acting along the line of the joining or the position vector, but in the opposite direction of the position vector. So that's how we can write this. Again, we can write this equation in terms of vector, r vector, like this also, r cube, then here it will be r vector. Okay, now look, this is the force which is acting along the direction of the, like along the opposite direction of the position vector. So that's why this force, direction of this force is given here. Now look, what will be the torque? Actually torque is responsible for the rotational motion. Okay, as in the linear motion, force is responsible for the linear motion. In case of rotational motion, since the planet is rotating around the sun, the torque about the sun, torque of the planet, so I can write torque of the planet about the sun, torque on the planet, torque on the planet, torque on the planet about the sun can be obtained by r cross f. Okay, now look, f is also along the r vector with a minus sign, and this is r vector already is there. So if I write this, see this is a constant vector. I'll just give them gms mp by r cube, and this is r vector. Okay, so you look, this r vector cross r vector will give rise to zero value. So what is the torque acting on this planet about the sun? Torque on the planet about the sun is zero. Okay, I hope it is clear to you what I have done so far. I have just calculated what is the force acting between, like acting on the planet due to the sun. So that is minus g ms mp divided by r cube r vector. It is directing towards the sun along the same position vector. Okay, in the same line of action. Okay, so look, if I want to calculate the torque on the planet about the sun, then I can write tau is equal to r cross f. Now f is also containing r vector, so since f and r both are in the same same direction, you look here, this is having r vector, here is also r vector. So this r cross r, since the angle between them is 0, so you'll get sine 0 0. So the torque on the planet about the sun is 0. So I'll write this result. Maybe I'll remove this part from here. Since we have learned the torque, so I'll write the final result that the torque on the planet about the sun is tau is equal to 0. So we know tau is given by dl by dt again, dl by dt. So this is from the relation between the angular momentum and the torque. So L is the angular momentum. So if this torque is 0, look, I can write this dl dt is equal to 0. So which implies that L, that means the angular momentum of the planet is constant. So the angular momentum of the planet is constant by direction and magnitude both. Okay, and see happens for happens for a closed and elliptical orbit. Okay, elliptical orbit or even circular orbit as well. Now look, this is one inference that the orbit will be either circular or elliptical, and also it will be a closed orbit. And we can prove, you can see the force acting, see force here, here is the gravitational force, and that is directly proportional to inverse square of the distance between the planet and the sun. So such kind of force actually will give rise to elliptic orbit. Okay, so inverse square, so here there are two things. One is the angular momentum is constant by direction and magnitude, and the force is inverse square. F is an inverse square square. Okay, inverse square force. Okay, it is like this force has the nature of inverse square law, so that's why we can prove from here. There are two things you have to remember, that you have to show that the angular momentum is constant, and that can be constant for an elliptic or circular orbit. And at the same time you have to say that the gravitational force is an inverse square, follow the inverse square law, or abide by or obeys the inverse square law, hence it will give rise to an elliptic orbit. So this is the proof for the inverse square law. Means, see, the force is gravitational force is inversely proportional to the square of the distance between the planet and the sun. That is the reason. So you will be learning various type of forces in your graduation, and you will see when force is something like kr to the power minus 2, or F is equal to k by r square. So kind of this force if you get, this is called inverse square force, and this will give rise to elliptical orbit. Okay, so this is how we can prove the first law, that all the planets move in elliptic orbits about the sun and keeping the sun at one of the foci of the ellipse. Now we'll recap the second law, and then we'll prove the second law. So Kepler's second law is actually also called law of area. I'll tell you why it is called law of area. See here, in the elliptic orbit, the radius vector which is joining the sun and the planet actually rotating, right? Rotating in this elliptical orbit. And while rotating, it actually covers certain area, covers certain area. You look here, this kind of this, okay, covers certain area in during particular time interval. Okay, so this rate of swept of area is always constant. So that is the Kepler's second law. Rate of swept in the area is constant. So the line joining the planets and the sun sweeps equal area in equal time interval of time. So this law actually comes from the observation of the planets appear moving. Okay, from this law also you will be able to find out that the sun looks like a planet looks like moving slowly when it is away from the sun, and it looks moving faster when it is near to the sun. So that thing comes from this particular law. So this can be proved from this law of area. Let us see how we can prove this law of area. The law of area. Okay, so to prove that, let us take a planet which is situated at P, and the radius vector, as we have discussed already. Radius vector, let us take radius vector this is the radius vector, or position vector also you can say, of planet with respect to the sun. Okay, sorry, this may not be actually we should not say this is radius vector, we should better say position vector. This is a position vector. Position vector, better to write position vector. So this position vector, and see the similar thing, the force of gravitation which is acting towards the sun, and the line of action of the force is the same as the position vector. So we can write this as GMSMP similarly by r cube into r vector, that we can write. Okay, now see, in this case the same thing we'll do. The torque exerted by the planet, sorry, torque exerted on the planet by this gravitational force will be further zero, right? That we have already proved in the previous slide. So this is 0. Then what was the corollary from here? This is L. L is the angular momentum constant. So this is what we have got. Now look, we'll do one thing. As we are saying that the area swept out by this radius vector or the position vector, the rate of area swept by this position vector will be always equal. So the line that joins the planet and the sun sweeps equal area. So this is the position vector which is actually joining the planet and the sun in this case. So suppose the planet was at any instant of time, the planet was at P and it moves to P prime. So planet moves from P to P prime in time interval delta Okay, and see in this case the speed, because this small time interval, so the distance between p and p prime is very small. So let us take this speed of the planet remains the same, that is v in both places. So now what we can do is that if we want to calculate the area which is being swept during this time interval, see, you have to find out the area of this shaded region. So you will get the area. Suppose that area is delta A, and that delta A can be obtained by the use of our knowledge of geometry. See, this is kind of a triangle. So this is the area of triangle SP prime, of triangle SPP prime, right? So this is the area. Now see this area for a triangle. You look, if I draw this SSP, okay, so this is kind of this, right? Okay, so this is S, this is P, and this is P prime. So how do you get? Look, this is R. This is, this we can treat as height. Okay, this may not be straight line here, but since this P and P prime, the delta t time interval is very very small, so that's why this P prime can be taken as a straight line, not an arc. So we can find out, see, half into base into height. So this height we have to find out. So half base into height. Sorry. So this height, that means this is PP prime. This height you have to find out. So PP prime, see, look, the speed is v, and the time interval between these two positions, like when the planet goes from p to p prime, it takes delta t time, and let us say the constant speed, it moves with constant speed v. So what will be the distance p prime? We know it will be v into t, delta t. So this is half into r into v into delta t. So what we have got? We have got delta A, that is the area. Okay, that is the area of this shaded region, which is covered or which is swept out by this position vector r in delta t time interval. Okay, so I'll just do one thing. I'll remove this portion because these are known to us already. We can write anytime if we want. So I'll just write it here now. So delta A, we have got half into r into v into delta t. Okay, so look, this portion I'll remove then to do the calculation over here. So if I multiply m in the numerator and divide with m, so there is no change in the equation itself. So we can write this is r p, this can be written as this into delta t, right? So if we write in terms of vector, if we write in terms of vector, this term area vector, this area to be a vector, we can consider the area to be a vector, and that vector can be written as P into delta T. Now, if we want to find out the rate of change of this area, then we have to find out delta A by delta T. So what we get? R cross P by 2m. So R cross P means what? R cross P is the moment of linear momentum, which is angular momentum divided by 2m. And what we had already proved in the previous case also, that angular momentum is constant in case of elliptic orbit. Angular momentum is constant for elliptic orbit. So L is constant and mass of the planet is already constant. So what we can say that this rate of change of area vector is constant. Okay, since L is constant, so it is also constant. That means, see, this rate of change of area vector means the aerial velocity. Aerial velocity. Sometime it can be written as aerial velocity. So thus planet remains thus the aerial velocity of the planet remains constant. That is, the radius vector joining the planet to the sun sweeps out equal area in equal time interval. Thus we can prove, like in this way we can prove the second law, Kepler's second law, that is the law of area. Okay, so this is the proof. So aerial velocity, that is del delta A by delta T is equal to R cross P by 2m. R cross P is the linear moment, moment of linear momentum, that is angular momentum divided by 2m. This 2m, m is the mass of the planet. This is constant, and also angular momentum is constant for an elliptic orbit that we had proved. That's how we can say the aerial velocity is constant. Okay, so thus we have proved the second law, Kepler's second law, or law of area. Now we will prove Kepler's third law, or this is also called law of period. Okay, law of period. Let us first learn the third law and then we will prove. What is the third law? It says that the square of the period of revolution of a planet around the sun is proportional to the cube of the semi-major axis of the elliptic orbit. Look, what is semi-major axis? Semi-major axis is this one. This is the semi-major axis. PA is the semi-major axis for an elliptic orbit, and this is given by 2 into A. And semi-minor axis is, so this is semi-major axis. Semi-major axis. And BC, this is 2B. That is called semi-minor axis. Minor axis. Okay, this is semi-minor axis. Now we have to prove the equation, or we have to prove the law. What is the law? If the time period of revolution of a planet, particular planet around the sun, is t, and semi-major axis is a, then it can be shown that t square, the square of the time period of the planet about the sun, is directly proportional to the cube of the semi-major axis. Cube of the semi-major axis of the orbit, elliptic orbit, or elliptical orbit. Okay, so let us prove this. So to prove this, we will first take up the revolution of a particular planet, suppose P, and it has mass small m, and it is revolving around the sun. Here suppose the sun is, okay, sun at the center, and this is, you can see this, we are taking as circular orbit first, circular orbit, then we will extend the law to the elliptic orbit. Okay, so in this case you look, the planet is revolving around the sun in a circular orbit of radius r. You can see radius is r, radius of the circular path, and v, small v, is the speed of the planet while revolving around the sun, and that is constant. Now look here, you have to find out this law. So let us first calculate for this circular orbit itself the time period of the revolution. So how do we find out? The total distance it can cover is the 2 pi r, that is the circumference of the circle. Circumference divided by the speed of the planet. Okay. Now look, in this case 2 pi r by v. Okay, very nice. Now we can, what we can do is we can square this out so that we get 4 pi square r square by v square. So this is very general circular motion concept. Now let us see for revolving around the sun, whether it is elliptic orbit or circular orbit, there you need a centripetal force, and that centripetal force will be obtained from the gravitational force exerted by the sun to the planet. So m v square by r, m v square by r, suppose mass is the mass, m is the mass of the planet, and v is the speed of the planet. So m v square by r is the centripetal force required for revolving around the sun if the circular orbit is r. Then actually this centripetal force is supplied by the gravitational pull or gravitational attraction exerted on the planet by the sun. So then we can write G ms into m divided by r square. Okay, so look here, m goes off, so we can write that v square is equal to g m s by r square, sorry r, one r got cancelled, so this will be alone with r. Now here we have got what is v square. V square is 4 pi square r square by t square. Okay, if we equate these two equations, so what we get? Compare these two equations. So v square is equal to this one, and here v square is equal to this one. So what you can do from this equation 1 and 2, we can write that 4 pi square r square by t square is equal to gm s by r. Okay, now from here, look, what we can do is we can I'll be writing here. See, from here we can write t square is equal to 4 pi 4 pi square r cube and divided by g into m s, which is the mass of the sun. So look, this term, the 4 pi square by g m s, this term is a constant term that can be written as k, that can be written as k. So we can write this k r cube. K is a proportionality constant. Okay, proportionality constant. So we can prove from here that t square is directly proportional to r cube. Here in this circular orbit, r is the radius, but this result can be equally extended to the elliptic orbit as well. But for that case, small r can be not can be it has to be replaced by the major axis cube of the major axis. Okay, so for elliptic orbit we can write t square is equal to, sorry, square, yeah, I'll write this. T square is equal to 4 pi square, then a cube by gms. Okay, so this particular term is a constant term, so this we can write as k a q, and this is t square. So this is how we can prove the third law, or the law of period. Okay, so what we have done, we have just first considered the circular motion of planet, and for the circular motion, planet has to be supplied centripetal force, and that centripetal force is actually coming from the gravitational attraction by the sun onto the planet. So from there we will get a relation between v and this thing, like mv square by r, right? Mv square by r is equal to gmm m s m by r square. So from here you will get the value of v square, and earlier also in this you have got v square. So you can compare two v squares and get the equation this. Okay, so this is how we can prove the Kepler's law, and we have proved all the Kepler's law, and today I'll be stopping it here, and this is how we finish the chapter. Next day I'll take up few numerical examples from this chapter, and then finally conclude the chapter. Okay, so I'll stop it here for today. I'll see you on Thursday. Okay, bye for today.